In this module of Chapter 3 on mortality, Module 3.2, I will cover the two main metrics of discrete mortality. Mortality can be expressed in both discrete and continuous form. The discrete versions fall into two main categories. First, that of probability. That is risk relative to the total number exposed. For example, 0.10 would be a probability of dying. And the second would be a rate. That is deaths relative to life years lived in specific periods. For example, 1 death per 10 life years lived. The differences between these two metrics are evident in their algebraic definitions, where Qx denotes the age-specific probability of death and, as outlined in the modules on life tables, equals the number dying in the interval x to x plus 1 divided by the number alive at age x. This is the probability of death. In contrast, mx, referred to as the central death rate, is equal to the number dying in the interval x to x plus 1 divided by the number of years lived from x to x plus 1 by those alive at age x. Note that the numerators of both of these equations are identical. Consider these examples of Qx and Mx computations using the same data. Suppose that 100 individuals are at risk over a given period and that 12 die. Thus, the probability of dying in the age interval of Qx equals 0.12. Using these same data, we note that the average number of life years lived in that interval is 88 for the individuals who survived the interval, plus an additional 6 life years for the individuals who died in the interval on average midway through. So the central death rate, mx, is computed as 12 deaths in the numerator divided by 94 life years in the denominator, or mx equals 0.128 deaths per life year lived. Each of the two metrics can be visualized in this Lexis diagram. Age-specific mortality, Qx, can be viewed as the ratio of the 31-year-olds in 2011 to the number who survived to 32 in 2012. In this hypothetical case, 2 died. The central death rate is visualized as a Lexis square containing individuals between 31 and 32 between the years 2011 and 2012. In this case, mx is computed using the 4 deaths relative to the total life years in the square. Age-specific mortality Qx and the age-specific central death rate mx are related by the formula shown here, that is, assuming average deaths occur halfway through the age interval, x to x plus 1. The values of age-specific mortality Qx and age-specific central death rate mx are similar at most ages. However, mx usually exceeds Qx at the very young and the very old ages. This is because the within-age distribution of deaths at these extreme ages are skewed to the left. That is, for example, most infant deaths occur shortly after birth and not midway through that first year, thus reducing the within-interval life years lived by individuals who die. That is, the average is not at the age 0 to 1 interval midpoint. This ends Module 3.2 on discrete mortality metrics. In the next module, I will describe, derive, and illustrate the continuous version of mortality referred to as the force of mortality.